YouTube. Yes, we're a few minutes late. We're going to blame technology.
As always.
Specifically, I'm going to blame Skype this time. With us, we have Alan Wolke W2AEW, which is his moniker, a good way to find him. And we have Ben Jordon, as always. How you doing, guys?
Very good. Really good to see you.
I'm doing good, hanging in there. And as I said, fighting with technology, but that's what we do.
So here's what's up, everybody. When Alan goes to do a screen share, his image and Ben's goes away. Mine stays. And there's no reason on earth why it should do that, but he can't do a screen share. So what he's going to do is he's going to be moving his camera. We'll just work through it. We got a lot of cool stuff to talk about today about care and feeding of your oscilloscope, which rule number one, we just came up with this. Don't take the oscilloscope in the bathtub with you. That's a bad thing to do.
Don't feed it water.
The way you just said that, Bill, sounded like Karen feeding. So feeding Karens.
Care and feeding, yes.
That's a fun thing to do.
Yeah. That's my north of the hemisphere accent, as we say. So, Alan, how you doing? We had you on once before. I think Ben wasn't in that week, and we had you on, if I remember right.
Yeah, we were talking about real-time spectrum analyzers, I thought.
That's right. That's right. We turned on the microwave and stuff. Yeah.
Yeah, and I did run through some hoops because I had the analyzer running in my home office downstairs, and I was using a VNC program to show it up here. And but at least I'm all up in the ham radio shack today. So.
Oh, very cool. Very cool. Yeah. So you have two places that you can work in your home office there. That's always cool.
Yeah, the home office is on the first floor of the house, and I'm up in a second floor spare bedroom right now. So,
right, and Ben's got his office, as you can see. It's a work in progress, but he's now got a dedicated workspace,
nice.
Which it sounds very cool. Yeah.
Yep.
So
Still
while we were side of it. Yeah. Well, part of the conversation everybody missed was while we were working on the Skype issues, the fact that the sign behind Ben either moves or it doesn't. And when it's not moving, it means technology has failed us and that Skype is locked up. So it actually became a valid, a useful point of test equipment stuff. So,
so before we
go ahead,
one very interesting artifact I noticed years ago when I started making videos for Altium. And I was editing a video one day, and I had actually taken some footage of me talking to the camera in an office with a window, and behind me through the window were some trees, and it was a really blustery, windy day. And I noticed while I was editing the video that the trees kept moving in exactly the same pattern and resetting. And I realized that they've actually basically looped the background to compress the data.
Wow.
And this was in the Adobe video editing software. I was like blown away.
Oh,
wow. So yeah, you would find the cells that tile heavily, that if in the tile you would see a heavy delta, right? And just tag that as background, I guess, or some moving background.
Yeah, it was just really bizarre.
Yeah.
Even I noticed it. But
insert my standard rant here about programmers and software, and it's just when the real problem is bandwidth, right? They're trying to solve the bandwidth problem, so I shouldn't get on them too heavy. So, hey, before we launch into today's thing, I did want to show one additional thing the last week. I'm not sure I saw a smoking gun last week. I certainly didn't see what I saw. I was able to drag up one more image using the scope as a digital storage scope. We were actually, last time, we were viewing it in fast acquisition mode, which is where the spectral display was coming from. But now I told it, hey, go to 1 million samples, and I was using a function of the scope called setup and hold, and I told it, when you violate setup and hold, trigger. Now, I didn't get real solid triggering, but I did catch this one image. My mouse won't appear on it, unfortunately, but you can see the green trace is RAS, and we get this almost asynchronous pulse on the address line. It starts slow and it ends low, but it has a pulse and some ringing. And that's probably what I was seeing ever so long ago. I was probably seeing an artifact more from crosstalk. It's possible it's contention, especially processors like the Z80. If you contend them, in other words, their outputs are fighting some other outputs, all of their outputs will reflect that because current inside the chip is starting to go haywire on it. So it may come out of the Z80 like this, or it may have been crosstalked on the PC board. But the conclusion I came to is the trace itself is not a crime against nature. It actually looks very much like the address line right next to it. In fact, they run parallel to each other. So this is probably a crosstalk artifact or possibly a contention artifact is what what we were looking at. And the bodge wire probably just lowers the impedance. And if it's crosstalk, it moves the source, it puts a parallel path in addition to the crosstalk, so it kind of swamps it out. So just kind of my conclusion I came to after all of that. So onward and upward though, Tektronix scope today, care and feeding of the scope. Alan, what do I mean when I say that? You know far more than I do about what we need to talk about.
I mean, the way I look at it is that a scope is a tool like any other tool, right? And it's important to know not only what it can do and how to make it do that, but it's also important to know what it can't do so you don't ask it to do something that it can't. Because if you do something improperly with the scope, asking it to do something or react a certain way in an improper way, it generally is not going to tell you, it's just going to lie to you. Right.
Okay.
Just like any other tool. I mean, one of the examples I like to use is like a circuit simulation, like SPICE, for example. Right. If you set up LT SPICE to put 1,000 amps through a 1N914 diode, SPICE doesn't know that you let the smoke out of that diode. Right.
Right.
But it's just going to tell you that the forward voltage is 7.2 volts or something like that. Right. So an oscilloscope is the same way. You've got to learn to understand the limitations of what the scope is and what its features are so that you can apply it appropriately and use it appropriately. So, and the good thing is that all these scopes these days will give you all the information about what they're doing. You just have to be smart enough to recognize what it's telling you and to see whether or not that's truly applicable to what you want and what you need for what the scope is doing. And one of probably the most common things is how to get signals into the scope cleanly, right? And that all gets down to probing. And this is something we talked about a little bit last week in terms of how probing that you were doing inside the computer, and then things like ground leads and all that kind of stuff.
Right.
And it just brought up a good topic. I thought at least start with that, but then there's a couple of other little hidden secrets that are kind of maybe buried in menus on the scope that could be really useful. And I thought we could cover some of those kind of things that'll take you from kind of an average scope user to a power user. So
now you're going to be showing us a digital scope today, but this applies to both digital and analog scopes, I'm assuming.
The probing piece certainly does. A couple of the tricks may apply more to digital scopes and analogs, but certainly the probing piece applies to regardless of what scopes you're using. So, so the first thought that I thought we'd go through is to talk a little bit about probing, because everybody hears, use a 10x probe, right? And you got your oscilloscope probe here, and it says it's a 10x probe. What does that mean? And how do we use it properly? And how do we set up a scope properly to use it? All of that can be really important. And so I guess I could ask people to kind of type into the chat if you want. If I asked you what does it mean to say a probe is a 10x probe, what does that mean? And sometimes you ask people, especially you ask 10 people, sometimes you might get 10 different answers. But the reason there's actually several reasons why you'd call a 10x probe a 10x probe, because number one, it divides the input signal by a factor of 10 in terms of what the scope is going to see. And you might ask why we're going to do that. I'll talk about that in a minute. It also essentially then multiplies the vertical scale by a factor of 10, right? Because if you're taking the signal down by a factor of 10 and you don't change anything on the vertical scale, it looks like you'd have to change the vertical scale to get the voltages to read right. Okay. So, and it also extends the bandwidth of the scope. So let's talk, or extends the bandwidth of the probe. So let's actually talk about why that is. So Bill, I don't know if you want to make full screen the little probe discussion document there.
We can do that.
Yeah. So, so what we're looking at here is just a little document. Let's see. Hopefully, I can't see the YouTube view to be sure it's being shown completely in the YouTube view here. But so this is kind of like what the scope input circuit looks like in a very simplified sense. You know, the vast majority of scopes below a couple of gigahertz of bandwidth generally just look like a 1 megohm termination resistor to ground, and that's shunted by some small amount of capacitance. Okay, usually somewhere between 10 to 25 or 30 picofarads, depending on the scope. Okay, and that's what you're interfacing with. So, for the most part, it looks like a pretty high impedance load, right? We don't have to worry about that. Okay, but so how do we connect that up? Why don't you scroll down to the next page?
I didn't realize I could do that till just now.
There you go.
Very cool.
So, well, why don't we just attach some wires, right? Well, number one, that gives you a lot of stray inductance, right? Because inductance, as you may know, is proportional to the loop area contained within the circle of that measurement, going from the signal input through the 1 megohm resistor back through ground, back to the circuit. The larger that loop area, the more inductance you have. And if you've got inductance, then that's going to affect your circuit, right? Especially depending on what frequency you're dealing with. And these long wires, because they're not shielded, can act like antennas. And will pick up all kinds of stray stuff from the air and things like that. So generally not a good idea unless you're working on really low current, or excuse me, low frequency work and things like that. So generally okay for low frequency work, but I wouldn't do anything beyond that. Just scroll down a little bit more. The next page. So okay, well let's fix that stray, try to fix some of those problems by making that connection from the scope to my circuit a piece of coax, all right? And this is your typical 1x probe, right? And say, okay, well that kind of solves the inductance problem for the most part because I've minimized the enclosed loop area between the ground return and my signal, so that's good. I've also shielded the signal wire, so I'm not going to pick up things, that's good. But my trade-off was that I've now dramatically increased the amount of capacitance that is seen at the probe tip to ground. And typical 1x probes will give you in the neighborhood of about 100 picofarads of capacitive loading. So will that matter to what you're measuring? Well, it depends on what you're measuring, right? So, and the impedance of the circuit that you're measuring and the frequency that you're operating at. 1x probes
can actually affect the circuit you're measuring too. That capacitance adding to. So imagine trying to probe an oscillator that you try to design it. Even at audio frequency, I would want to design a very low THD oscillator for test purposes. The moment I put a 1 times tip on that, it's going to shift the frequency or stop oscillating or maybe even start oscillating. And why does it work when I measure but not when I'm not?
Yeah, right, and that's 100 picofarads of capacitance. So if it works when you put the probe on, it does when you take it off. Solder a 100 picofarad capacitor right there, and then it'll work.
Right.
So, right. But so it solves some problems, but it also adds this capacitance problem. And for the most part, with this like a 1x probe, which is really nothing more than a piece of coax with the probe tip on it for the most part. There's a couple other minor differences, but we won't get into that. Generally good for to 5 or 10 megahertz at most. And beyond that 100 picofarads of capacitance is just going to be too heavy of a load. Is not going to really be helpful anymore. So let's just scroll down. I guess it's the last page now. Or almost, it might be the last page. Let's see. All right, so almost the last page. So what we do with a 10x probe is there's actually a 9 megohm resistor in series. Now, Bill, I've got my little Skype window up and it's showing Ben full screen and not what you're sharing. So I'm not sure what's showing up on YouTube.
Yeah, so it's showing the one with the 9 meg resistor in series with it.
Okay. Oh, so when you speak, okay, I've got the speaker view that's popping up here, and that's why. So when you speak, that's kind of got it. Okay. So we stick a 9 megohm resistor in series with that probe, or with the probe tip. Okay, right at the probe tip. So what's that going to do for us? Well, it's going to stick that 100 picofarads of capacitance on the other side of a 9 megohm resistor. So the circuit's really not going to see it, right? Because even if that 100 picofarads of capacitance was something much larger, it's still sitting on the other side of a 9 megohm resistor. So it's not really going to affect the circuit. Well, that's it. I fixed that problem, right? But now I introduced another problem, okay? So at very low frequencies, we'll get a 10x voltage division between the 9 megohm resistor and the 1 megohm resistor inside the scope. Everything works fine. But as soon as we get up above just a couple of kilohertz, that 10 to 20 picofarads of input capacitance on the scope, its capacitive reactance starts to be lower than 1 megohm. And what have we created? An RC low-pass filter.
Right. I was going to say you put a pole in there when you did that.
Exactly. So now I've got a low-pass filter. So shoot, I got rid of the capacitance, but I'm low-pass filtering the signal going into the scope. So the last slide, okay, it'll kind of show us how to deal with that. Okay. So
yeah, come on, it's not scrolling down.
All right, you got
hang on a second. I have to put it in as a new one. And everybody, this is due to the Skype problem we were having earlier. So, so let me grab one more image here.
Okay.
You put a matching 0 for your pole.
Basically, yeah. So what we stick a capacitor in parallel with that 9 megohm resistor. And we have to size that capacitor so it and the input capacitance of the scope have about the same ratio as the 9 megohm and 1 megohm resistor. So we have a 10-to-1 ratio in the resistors, and we want essentially a 10-to-1 ratio in the capacitors. Okay, but the other way around. Okay, so
why you have an actual.
Yeah, exactly. Because now at low frequencies the 10x division comes from the resistors. At high frequencies, the 10x division comes from the capacitive voltage divider. And because the input capacitance of a scope is not consistent from scope to scope, we can't just use a fixed capacitor around that 9 megohm resistor. We need to make it adjustable so we can compensate the probe to match the input capacitance of the scope. So let me see, where did I put it? This is always the problem. So I don't know if you want to put me back on video again, but...
Yep, you're on.
All right. Everybody know where that little tool is that came with your probe? The compensation adjustment tool? Is it just buried in a drawer somewhere? Do you actually have it and even know what it is or where it is? All right. How many of you actually have compensated your probes? And
there's mine.
There you go. Okay. So the reality is that a lot of people forget about these things, or they compensate the probe once and then they wind up using the probe on 3 other different scopes, never even thinking about compensation again. Now, if all those scopes are the same model, then you're probably going to be okay. But if you go from a 500 megahertz scope to a 100 megahertz scope to a 300 megahertz scope, the input capacitance is probably different and you're not going to be compensated right. And the errors that you get in terms of amplitude errors can start to occur at surprisingly low frequencies, like as little as just a couple of kilohertz or more. Okay. So you might say your amplitude readings might not be off by much, but they might be off by 10 or 20%. And will that matter? Yeah, it might, right? So, so probe compensation is actually a pretty important thing and something that not a lot of people, unfortunately, think about. So, I see some comments here that yeah, every time I swap scope probes or move the scope, yeah, that's when you want to actually compensate the probes. Now, so that's one issue with the probes. And then, like, if we look at this probe here, this is a Tektronix P6139. I don't know if I can get the thing to focus on that.
Yeah, back it up just a bit.
Yeah, so...
Yeah, it's not focusing. Yeah, but...
So P6139, and its probe, there's a little hole right there where I do the probe comp, okay? I've got another one here. This is a TPP 0201, and it's got the little compensation adjustment, right there, okay? So that's one thing that's important to do, and we'll run through that. I'll show you actually how to do it. Now let's see. Do you want me to try to share my eScope screen just so we can kind of keep that full screen? Actually, you know what? I'm probably better doing this one with the camera because I want to kind of show what I'm doing with the camera.
Yeah. So real quick, I have my TPP 1000, and I'm not seeing a hole for the.
Yeah. What's up with that? Let's talk about that in a minute.
Okay.
Okay, but that's a very important point. All right, so let me switch my camera here to switch to the camera that's pointing to my scope. So that's the HD webcam. And let's turn that one on. Let's see, does that work? All right, so you should see the my scope here now. Okay, so let's do this. So I'm going to take this P6139 probe. I'm going to stick it right here on channel 2. And let's turn off channel 1 for the moment, turn on channel 2. And I'm going to go into my trigger menu and tell it I want to trigger on channel 2, so I'm all good to go. So now most scopes, looks like this one, have a probe compensation signal on it. On this scope, it happens to be 2 little loops over here on the side. Other scopes will sometimes be somewhere on the front panel. And what that signal is a 1 kilohertz signal generally. It's not a precise 1 kilohertz, so don't get upset if you measure it and it's 990 hertz or 1.02 kilohertz. It's not intended to be a precise frequency reference, okay? So it's intended to essentially give me a square wave, okay, that I can actually use on the scope for compensation. And what we're doing, I'm just going to adjust this on the screen here a little bit, and let me make it a little bit bigger, pull it down here. So we use a 1 kilohertz square wave because the 1 kilohertz is a low enough frequency that the 10-to-1 voltage divider is dominated by the resistors. Okay, so the steady state of the highs and the lows of the square wave are going to be dictated by the 10 megohm resistor. Okay, the high frequency it's a square wave, which means it's got energy at its odd harmonics, third, fifth, seventh, etc. And the faster the edges, the higher the frequency of the harmonics we have. If we improperly adjust my compensation here, I'm going to go into and just tweak you can see what happens if I don't have the probe adjusted right. I've low pass filtered that edge. Okay, you see I've got kind of this low pass filter response here, this little tail. That means that
that's on a 1 kilohertz too. I mean, that's a pretty effective
compensation. Yeah, it didn't affect the final settling point, but it affected the first 5 or 10, 20% of it. So that means that at a couple of kilohertz, I would have had a poor frequency reading. And then similarly, if I take I'm going to move my thing here so you can kind of see what I'm doing. I'm sticking the adjustment back into that hole, get my arm out of the way. We adjust the other way. See what happens if I make that capacitor too large. I pass too much of the high frequency energy through, and higher frequencies will measure higher because they're going to be divided by less than a factor of 10. So the idea with probe compensation is to just adjust that to give you a nice perfect square wave, okay, or as close as you can get. And you've got to do that anytime you put that probe on a new scope, right? Because the input capacitance of that particular scope might be different. This one here says it's 1 megohm and 13 picofarads, relatively low. A lower bandwidth scope like 100, 200 megahertz scope might have 18 or 20 or 25 picofarads of input capacitance, and you'd have to adjust that probe differently. So, another common question is like, well, okay, I've got a 10x probe that says it's a 500 megahertz probe. Can I use that on my 100 megahertz scope? Or the other way around, I've got a 500 megahertz scope, but my 10x probe says it's only rated for 100 meg. Can I use that? And the answer is a solid and firm maybe. Okay, right? And because it really comes down to the range of capacitance that compensation adjustment can account for and adjust for is limited. Okay, so a particular probe, that probe compensation adjustment might only be able to compensate for 10 to 18 picofarads. And if your scope input capacitance is 22 picofarads, you won't be able to properly compensate it. And vice versa, it might be skewed the other way. Now, the probe is never going to increase the bandwidth of your scope. So if you use a wideband probe on a lower bandwidth scope, you're not going to magically get more bandwidth. If you can compensate it, it'll work, and it'll work up to the rated frequency range of the scope. Okay, so whichever is the lowest common bandwidth rating is the thing that's going to dictate the bandwidth of your combination.
Do you recommend actually having the scope probe be overrated for the scope? Like if it's a 100 meg scope, having a 150 meg probe, or does it not really matter if it's a true 100 meg probe? Which I assume means it's 3 dB down at 100 meg.
Yeah, so I guess, unfortunately, the answer to that depends a little bit too. And the reason for that is that when Tektronix rates probes, if a Tektronix rates a probe at 500 meg, It's rated at 500 meg, so that if you put it on a 500 megahertz scope, you get 500 megahertz bandwidth. Okay.
Okay.
So it's not. So it's really. So the probe itself is in actuality wider in bandwidth than what the rating is. The intent is that the combination gives you that bandwidth. But
Okay.
that's the way Tektronix rates it. If you buy a probe from, Joe Blow's probes, from AliExpress or something like that, and it says it's a 100 megahertz probe, the probe itself might be 100 meg, and you put it on a 100 meg scope, and you might be down at 70 megahertz when you do that, right? So overrating them is okay to help avoid that if you don't know the source of the probe, but as long as you can properly compensate it, you'll be in good shape. Okay?
Okay.
So something else I'll mention too here, and let me see if I can actually get it close enough in on the screen to see that without getting a glare. Let me see here. Let's see, there's a glare if I do it there. You see that the scope scale says 500 millivolts a division. Okay.
Yes, I see that.
Right. If I pull the probe out, see how it switched to 50 millivolts a division?
Right. Right.
Okay. So the scope knows that I plugged in a 10x probe. How does it know that? Here's the other little trick. Okay. Tektronix had kind of pioneered this. Some other manufacturers do it.
Yep.
But if we take a look at this probe, you can actually see there's a little spring-loaded pin right here on the side of the BNC connector. Okay, that pin is like a little 10x identifier, and even other probes like 100x probes will have a different value resistor in there that actually do it. But it actually connects a resistor up to the little shell that's around the perimeter of the BNC connector, and that's what tells the scope what probe you're using. Okay, that's a 10x probe. Some probes, some 10x probes, like this one here, this is a that TPP 0201. Notice it does not have that little pin like this one does. All right. So if I plug this probe in, this is a 10x probe, but the scope doesn't know that. Okay. So when you're using a scope or a probe that doesn't automatically sense the 10x, you've got to account for that yourself when you're setting that up if you want to get accurate readings. And one way to do that, let me see if I can actually show that on the screen here.
I was going to say on the MDO, so you're showing us an MDO 3000 scope too. We haven't talked about that.
Right.
But you're about to show us that you can set it up in a menu so that you don't have to manually. Okay, very good.
Yeah, so if I bring up the channel 2 menu, the vertical menu, that brings the menu up down here on the bottom. And in this case, if I hit more, I see fine scale, I see offset, I see position, and I see probe setup. And you see it says attenuation. It might be, I don't think the colors might get blown out here, but it says attenuation 1x. I would have to adjust that up to 10x in order to properly set the scale for that scope. Now your scope may be different, the menus that it has may be different, and even some of the old analog scopes oftentimes had two scales next to the vertical knob to show you the 1x scale or the 10x scale. So you would just have to kind of pay attention to whichever one you're using. Okay.
Got it.
So you do have to kind of make that adjustment when you don't have the types of probes that automatically set themselves up. Okay.
Now on your scope, I see about 6 little lands for that pin to touch. What are all those different?
All of these guys?
Yeah.
Yeah.
Are they different probes?
Yeah, there's actually a couple of different purposes, and one of them is for the reason that you mentioned, right? You said you've got one of these TPP 1000 probes, and there's no probes, no compensation adjustment for it, right?
Right.
Also notice this probe has got a pin, but it's in a different position, so that connects to one of those things. So these probes actually have a small little EEPROM right in here, and when you plug
Which answers the question somebody just asked. Yep.
Yeah, so when you plug it in, let me kind of bring up that channel, bring up the menu on that one, and if I go to the probe setup on this guy, you can see it actually tells me that it's a TPP 1000 probe. It knows the serial number of that probe, it knows it's an X probe, and it knows that it's been compensated. Well, how has it been compensated? I haven't touched a screwdriver on this thing, right? Well, the way you do that is these probes can be compensated automatically by the scope. Well, semi-automatically. What you do is you connect up the probe to that compensation signal over there, and then you touch this button here that says compensate probe, and it does the adjustment for you. And then what it does
Wow.
is it takes the coefficients for the filter to compensate that probe and stores them in a memory right behind the channel of the scope. So every time you plug that probe in from that point forward, it says, oh, that's this probe. I know how to compensate that, and it applies those corrections to it. So what I always tell people, if you get a scope like this that has this kind of semi-automatic compensation process, it takes the 10 minutes that it takes to take every one of your probes and compensate it on every one of the channels of the scope. And you only ever have to do that once if you're always just going to use that one scope, because from that point forward, each time you plug that probe in, it's going to recall the compensation settings for that particular scope.
That's very nice.
Yeah.
Very nice. I just, something else that's a key difference between a really good, solid brand like Tech compared to cheaper ones.
And,
like
I was going to say, don't say it.
10 years ago when Rigol was just new, and I thought, I can't believe there's a $400 oscilloscope. And you'll see that one of the key differences, this one is still back in the dark ages with the capacitor is actually in the tip.
Yes.
So I'm curious how that's achieved when you adjust or compensate the probe, but it's done at the connector end.
Yeah. That's a good question. And the reality is that the 10X probes internally are, at least these higher performance probes, are more complicated. Okay. And what they generally have is they do have a fixed capacitor across the 9 megohm resistor. And then in what we call the comp box that connects up to the scope, there's actually a little bit of an RC network in there. And the capacitor you're adjusting is part of that RC network.
Cool.
Okay,
Yep.
So you're effectively still adjusting the same capacitance ratio, but you're adjusting the ratio because you're adjusting capacitance at the other end as opposed to the probe tip.
Yeah.
end.
Yeah,
Okay.
we're using the engineering principle at, it's like when you look at systems,
Mm-hmm.
linear systems, it doesn't matter. It doesn't really matter. Like, it matters if something is in a feedback loop or if it's in a main gain stage.
Yeah.
But within the main branch of the system, you can put things anywhere and you get the same outcome, basically.
Right. Yeah. There was a question in the YouTube chat, is this probe that we're talking about, this TPP1000, isn't this an active probe? And it really isn't. The active probes connect the same way, and those other pins that you see above the BNC connector are power connections and things like that for when you actually do use active probes. But all of these TPP stands for Tech Passive Probe. These are all passive probes. Okay. So they just happen to be able to communicate to tell them what they are, and then the compensation characteristics essentially get stored in the scope. There's no memory in the probe other than the serial number and the model number for the probe. So. But
Hey, Alan, I brought up my e-scope, and I'm actually trying to switch to the probe setup, and I'm having a little trouble doing it.
Okay.
The A knob does my fine scale gain, but I don't have the ability. Can you show us real quick on yours how to get to the probe setup position?
Yeah. So if I bring up the vertical menu, right?
Vertical, right?
Okay. And then over here where it says more,
right? Got that.
Push on that, and then it cycles through the fine scale, offset position.
How do you cycle
setup.
through? That's why I'm having trouble.
Just by hitting the more button again.
Oh. See, okay, yeah, another.
Yeah, it's the one deviation from using the knob to do everything on this on this interface. That's one of the deviations from that is you actually will cycle through it with that. Okay.
Yeah, I don't seem to be able to do it from the electronic menu.
Oh, I've never tried it from eScope, so.
Yeah, it because the more button, there's no way to press the more button in the eScope.
Yeah. Okay. Actually, you can. You
how
put
do I
the
do
mouse
that?
right over where it says more, right on the graphic, and hit it.
Oh, you know what? I'm sitting there clicking on the image of the scope, not the scope itself. That's my fault. Okay.
Yeah. Okay.
Very good.
Yeah. Okay. So
there's the probe
again,
setup for everybody.
Important care in feeding, is a lot of it has to do with probes. Okay. And getting the probe set up right and compensated right will ensure that you get good, accurate measurement results. Use 10x probes whenever you can, and 1x probes when you need to, either for very low level and low frequency measurements where you can't maybe afford to attenuate the signal by a factor of 10. But then just keep in mind that you're not going to get any more than 5 or 10 megahertz of bandwidth at most with a 1x probe. Okay.
So on my menu, I also have a deskew. Is this a good time to talk about that?
Yeah, so we could talk about deskew. Because there's a fine scale as an offset, which I do want to talk about, offset and position. But let's talk about deskew. What deskew does is allows you to set up a time delay that you can add or subtract from that channel. So let's say, for example, I had a voltage probe on one of my scope inputs and a current probe on the other input, and I want to use that to measure power, for example, through a device. The voltage probe might have a different propagation delay from probe tip to the scope input than the current probe does. All right, so you may have to apply a skew to them to make them line up in time, especially if you got voltages and currents that are varying over time. Or if I've got different lengths of cables connecting to different parts of a circuit that I'm measuring, and you want to measure, what's going on at a given instant in time, you got to make sure that the signals that are present at the scope represent the actual timing location at the circuit that you're measuring. Yeah. So that allows you to account for the propagation delay differences between your probing and cabling methods between your DUT and the scope input.
Okay.
All right.
And it's a true
de-embedding of the test plane.
Yeah, it's basically a time domain de-embedding, basically. Yeah. So you may run into that. What's interesting, you might notice that for this given probe, that it knows that I've got a TPP 1000. It knows that probe has got a 5.3 nanosecond delay from the probe tip to the scope input. So for any probes that the scope recognizes, it'll actually tell you what that propagation delay is. And there's a button here to actually set all deskews to recommended values. So if I had multiple probes in here, it can automatically set up to those nominal values for you. So pretty cool.
Yes. Yeah. Very cool.
So one other thing I wanted to mention, there's two more things I really wanted to talk about with probing. One is the dreaded ground lead length.
Let's talk about that.
All right. So let's go and take a look at.
Yeah, because Alan and I have been talking about this off camera a bunch. And in particular, last week when I probed the board, I had this, I call it an abomination onto hell. This is a really long probe length that came with my TPP. I used it because I knew I could get away with it on last week's measurement, but the week before I used the ground clip that Alan's going to show us here in a second. Okay. But what I'll say I've done is I've ordered 10 of these from eBay, and I'm going to make up a set of shorter ones with first micrograbbers. So I'm going to make up 4 short ones with micrograbbers and then 4 short ones with alligator leads so that I have a choice, because this 5-inch, if I had to guess, I wouldn't look at something over 100 megahertz with this if I was actually looking at rise times and settling times.
Yeah, so the way to think about that, remember what we said about inductance? Inductance is proportional to loop area.
Look at the size of that loop, yeah.
Right, so if I connected this guy to a circuit point and a ground over somewhere else, I've got a nice big loop area there that looks like an inductor in series with the ground. Now the probe tip has got input capacitance, right? So what happens when you put inductors and capacitors together?
You get a resonance.
You create resonance circuits. And what happens with resonance circuits? They can ring.
Right.
They can ring. Okay, just like that. Okay. So using a shorter, now what's interesting, if I took that ground lead and I wrapped it around the probe tip like this and connected it up, that would tend to reduce the inductance, and actually the ringing would get better. But it's still not a fix. Okay. It's kind of a
right.
So what do we do about that, right? Well, these are the connections I have. Well, the probes themselves, you can pop off this the witch's hat here, and now you've got kind of the raw probe tip available to you. Okay, but what's interesting about that, if you look carefully, you see there's a exposed kind of conductor area ring right around this probe tip. That's actually ground. In fact, if you unscrew this probe, you can actually see this whole thing is all ground, right? And you can see the spring clip here for the ground lead is just clipped onto that. So we can pop that off. We don't need that right now. I can put my insulating collar back on it. But with your probes, should have also come a little Ziploc baggie like this, okay, or maybe a little plastic snap top box with these little spring tip probe ground adapters like this guy right here. See if I can get that in, kind of focused in here.
Yeah, I'm trying to focus one also. Yeah.
Yeah. So we can actually see it's kind of like a spring. Almost, I was going to say it was a spring steel, but we discovered that they're solderable, so it may not even be steel. Okay.
Yeah.
But what it is it has a little spring, a little coil at the one end that I can slip over that ground ring, and now I've got a very short, very low inductance ground right next to the probe tip. If you don't have these things, you can make them. I'll take leads off of the stiffer leads off of like a leaded capacitor, and I'll wrap one around and do it that way. Maybe even solder that down to the board and just slip that, slip my probe right into that to get a nice low impedance ground. So let's take a look at what happens if I use that. Let me kind of show you what I'm probing down here. Okay. So I'm probing this little test board down here, and I've got that long ground lead on it. And the signal I'm probing is about a 2 nanosecond wide pulse, and that's what I'm looking at here. So I'm at 10 nanoseconds of division. Let me kind of pop that over and maybe move that signal over here a little bit. Okay. Now, it might be better to actually look at the whole thing there. So there's my little 2 nanosecond wide pulse, and I see all this little ringing and stuff going on here. And you might say, well, that's really in my signal. Well, the reality is it might not be. So if I pull that probe off of here, and let's pop off the witch's hat and stick this little spring ground adapter on there, get that kind of on there good and tight. Let me pull off my ground lead. So now I've got this guy, and let's connect this guy up just to ground and my probe. Now look at that result, right? Very little ringing there. So what's there is probably real, okay?
Right.
And where that other ringing that we saw that extended out for 20 or 30 or 40 nanoseconds was all just ringing due to that LC tank circuit that I had connected up by using that long ground lead. Okay.
Right.
So you've got to watch those ground lead lengths, to ensure, especially if you're looking at fast edges and things like that, that's the kind of thing that's going to give you the best result, because where that inductance is going to matter is at higher and higher frequencies. But even if you're not working at stuff that's running at a gigahertz, you might be working with clocks that have got sub-nanosecond edges. Right? Yeah. Those sub-nanosecond rising and falling edges have got energy out at hundreds and hundreds of megahertz, where that inductance can start causing that tank circuit to ring and cause aberrations in your circuit. Okay, so you might be looking and trying to trace down what's the source of that problem. I got all this ground bounce going on, what's happening, and it might truly just be to your probing technique that's causing that. Okay,
right.
So that's certainly another thing to think about. And
one of the alterations I'll do on that is I will, if I'm working with a TTL chip, I'll extend that ground over to that pin 7 or that pin 8 so that I see ground the way the chip does.
Yes.
So I don't pick a ground better than the chip gets. I try and pick the same ground the chip gets if I'm being real accurate.
Yeah, when I talk about things like transmission lines and things like that, you have to remember that if you have a transmission line, and I think you've talked about this in past shows, if you have a transmission line that's scooting its way across a ground plane, the image current or return current follows a path underneath that line, even if it's not the straightest path back to ground, right? Because that's the lowest inductance path, therefore the lowest impedance path.
Lowest impedance, right.
So you really want to kind of see what the chip is seeing, right? So kind of probe it at the same point where its return signal is coming back from wherever it's driving to. So
right.
So
last week, probably the way I was able to get away, I shouldn't say get away, but I was more comfortable using these big long leads, is the ground that I did use was really, really good. It was the ground reference for the board. Mm-hmm. So I'm going, well, I've got a long lead, but at least it's to a good ground, not a bad ground.
Okay. So
it's a good pool of water. Yeah.
Yeah. So there's one other.
It just goes to show like the limitations of the 80s, the chips we were dealing with. Packages.
Yeah.
Like the 6502 parts, they actually have the ground and VCC on opposite corners of the package in some cases. Well, these days we know that's the worst case for impedance, for inductance. and we try and put our VCC and grounds next to each other.
Yeah.
Would you say, Ben?
It depends on the chip, but if you're still dealing with glue logic, they still follow the old footprint patterns where you have VCC on the top right and ground on the, even if it's a surface mount package, but at least the packages are smaller, so we're dealing with smaller loops.
Yeah, usually the best way to get around that is you're going to have a ground plane on the board, and you're going to put your decoupling cap right at the VCC pin. So that extends the ground right to that point, and the return currents can come right through that capacitor back to the supply. So,
right.
So I was going to bring up one other interesting trick that not a lot of people know about, and it's something that can really help you, especially if you're looking at things like power rails and things like that. So I'm going to switch what I'm looking at here on the scope. And what I'm probing now is a 3.3 volt power supply. Okay. So if I look, you see kind of right over here, there's my, if I get over here, there's kind of my ground reference, right? So if I pull the scope off, right, there's my ground reference. I'm at 500 millivolts of division. So if I go up here, there's my 3.3 volt rail. So, well, if I want to, I'm at 500 millivolts of division, I'm not getting a lot of vertical resolution around that rail. What if I want to zoom in on that and see what's really going on, right? Now, you could, with digital scopes, you can zoom in, but that doesn't improve resolution, right? Because remember, the 8 or 12-bit resolution, the ADC, is spread out over this whole entire range of the scope. So if I did a vertical zoom here, you're not improving resolution, right? It's just a magnifying glass, okay? So you really want to be able to reduce that vertical scale. So there's a position knob that I can move to kind of change the position of that waveform, right? And I can only move it down so far. But now, okay, let's go down to a lower scale here, okay? 200 millivolts of division, my signal is now up above the top of the screen, and my position control doesn't take me down anymore. So what do I do? Let me go back to
with the AC.
Well, you can go to AC coupling, right? And that's fine. So if I go, let's go do that. So let's go vertical scale, switch to AC coupling. Okay, now my signal is centered around ground because I've eliminated the DC content, and I can zoom in and go to, say 50 millivolts of division and see all that. But what's the problem with doing AC coupling? The problem is that you lose your DC information. So if you had something that was loading that power supply and causing a little bit of power supply sag, you wouldn't see that.
Yeah,
or if you had some sag that was going on at a low frequency as the chip is changing modes or something, you'd only see the edge of it. You wouldn't see the extent of it.
Yeah.
Okay.
Right.
So
now, aren't you putting a pole in there also when you do AC coupling? It's going through a capacitor. Aren't you also affecting the high frequency response as well?
Now the AC coupling is designed. You're gonna cut off the low frequency, but the high frequency is generally still going to be okay.
Okay.
It's the low frequency that you're losing, and you're effectively losing the DC contact. So let's go back to 500 millivolt division DC coupled, and adjust my offset down so I can see my waveform again. So most digital scopes also have an offset control. Offset and position are two different things. You'll notice as I was adjusting my vertical scale, it's expanding and contracting around my reference point, which is at 0 volts. But if I go under, again, it's hidden under a menu. If I go under a menu, there's a menu item called offset right here, and it's set to 0 volts right now. If I adjust that offset value, okay, let me adjust that offset value, and as I bring it up, you'll notice that my signal is coming down, and I'm going to bring it down I'm going to add enough offset until my DC level is sitting right at my reference point. So now that I'm essentially right at or very close to my reference point there, all right, I can adjust the position to put that back in the center. So now, in this case,
put a variable voltage source in series. With
exactly. I added an offset or subtracted an offset away from what the ADC is seeing. So now that's my reference point. So now when I adjust my vertical scale, it's going to adjust around that point. So it's scaling up and down above, in this case, 3.35 volts, which is where I dialed this into. So now I can dial up, and now there's my 50 millivolts of division. I still have the DC content. So if I see a sag or something like that in the power supply, I'll see it, and I can also make the other measurements on the noise and things like that. So a lot of people don't know that that offset is actually there because it's often hidden behind a menu. On some scopes, and I wish this one did it, push buttoning the vertical position knob will switch toggle you between position and offset. But a lot of scopes don't do that. This scope does not do that either.
Right.
Okay.
Right.
But there are scopes that actually do have a toggle between the offset and position functions right on the front panel. But otherwise, you got to go looking for it in the menu. But it can be a really useful thing when you're trying to debug power supply loading problems and that type of thing, and understanding both the high frequency and low frequency content of noise and disturbances that are on some DC offset. And even if you're dealing with like logic signals like LVDS, right? LVDS has some common mode voltage, right? If you set the offset to be right in the middle of the common mode voltage for your LVDS signals, then you can kind of set the scale appropriately, on the screen without having to mess around and maybe run out of position range, okay, by adjusting the offset that you're going to scale around. So,
right. Now, linear scopes don't really do this offset, right?
You mean analog scopes, yeah.
Yeah, analog scopes.
Yeah, they generally don't, because what we're doing is we're kind of optimizing what goes into the analog to digital converter, right? On the analog scopes, generally the position knob has a lot more range, okay? Because if you adjust the thing to be, if the signal is 8 divisions above the screen, you probably have enough range in the position knob to bring that back down. On the digital scopes, you don't have that.
That's what they taught us to do with the analog tech scopes when I was in college in the early 90s. We didn't, the college I went to didn't, they had some phosphor scopes that were just coming in.
Right.
But that was how they taught us to measure, was using the position. Yeah.
Right, right. So the position can be really helpful because it allows you to scale things around. So I would call this the reference point, or also even call it the vertical expansion point. Okay. Because I'm expanding and contracting the scale around that point, okay, which by default is ground, but it doesn't have to be by changing the offset. That brings up, I guess, one other thing, again, just understanding what the scope is showing you. Usually up in the scope, you will see a similar caret, if you will, okay? In this case, it's a down pointing caret right in the center of the screen. That's the horizontal expansion point. So what that means is if I make changes to the horizontal scale of the scope, it's going to expand and contract around that point. Okay. Most of the time, that point and the trigger location are the same location. So if I move the position, okay, if I move the position knob, okay, we can see oftentimes, now in this case, when I'm moving position, it's moving the trigger location, but not the horizontal expansion point. So if I scale, now I'm scaling around that horizontal expansion point. As I get finer and finer in, my trigger is way out over here somewhere. Okay. But this will help you sometimes to be able to view something that may be distant from the trigger by separating out the horizontal expansion point from the actual trigger location. So they're coming to get somebody.
Your scope has an audio function, mine doesn't. Yeah.
So, but yeah, so there's a lot of things the scope will tell you that once you learn what those little icons mean can be really helpful. The scope displays will often tell you obviously will tell you what the vertical and horizontal scales are. Will also tell you what sample rate the scope is running at, what record length the scope is using. In this case, my trigger to the horizontal expansion point delay value is being shown right in here. So learning to recognize and understand what the scope is actually telling you on all its little readouts can help you get the most out of what the scope is giving you.
So on my scope, I had set the record length like up to a meg or 10 meg, whatever the max is. Yep. And I was wondering why my scope took forever to do simple things. And it was just basically operator headspace, as we used to say in the service. Yeah. I set it back to like a low value for normal mundane things, and it works just fine. And I set the record length way up when I am capturing huge records. And
Bill, that actually brings up a very interesting point, because Tektronix scopes generally work that way, and actually for a very good reason. Because, like I said, if you set the record length to 10 million points, it's got to deal with 10 million points, right? And process and move that around. You will find there are manufacturers of scopes where you set up a long record length, and you go to make a measurement or do something, and it's really fast. How is it doing that, right? How is it moving that data so fast? What it's doing oftentimes is it's making the measurements on the displayed points, not the actual waveform record. So if you captured a 10 million point record that has a bunch of really fast edges on it, and if I tell a Tekscope to go make a rise time measurement, it'll actually go measure it, even though that rise time might only occupy a pixel on this display. It'll measure it properly because it's using the waveform record. Some scopes actually use the displayed points and won't be able to give you that measurement, or they'll lie to you and they'll give you an incorrect measurement because it's making the measurement on a decimated set of samples.
Software people.
So a complaint that we hear sometimes is that the Tekscope is slower than brand XYZ. And it's oftentimes because of that, because we choose to always make the measurements on the waveform record because that's the accurate way to do it. It's not the fastest way to do it, but it's the more accurate way to do it. So.
Yeah.
Right.
Can you believe we're at 12 o'clock already?
Well, if you guys are okay, I'd like to keep talking. Are you guys good for another 15 minutes?
Sure, I'm good.
I can go a bit longer. So let's do it.
So one of the questions from the chat channel was, what do you do if you don't have a ground near where you're trying to measure? And that's such a complex question. I didn't want to try and type it into the chat channel. My initial answer is, well, you're screwed. Not just in your ability to measure, but you should have ground close to your high-speed signal for the very reason that Alan mentioned and that Ben and I talk about, which is the return path needs to be close to the signal path. We tend to forget about the return paths.
Yeah, well, I think the issue oftentimes when that happens is not that there isn't a ground nearby, but there's not a ground nearby that you can actually get to with a probe.
Right.
Because you might have a buried ground plane, but if you haven't exposed that ground plane somewhere nearby, then you've got a compromise there. So it's one of those things when you're designing PCBs is to take the time to throw some ground vias in at the ends of your lines and things like that, just to create convenient test points to get good, accurate probing measurement results. So.
And even to that point, we're putting stitching vias for any signals that we care about half the time anyway. So all you need to do sometimes is make sure they're not tented.
Right. I was just getting ready to say that.
The via pad, you've got your ground point built in there.
Yeah, and get that little spring tip and punch it right into the via,
So, and if you want to be real careful about your ground, you might not even use a via, which can add all kinds of antenna and capacitance. You might just have a surface mount pad, depending on what your layout is.
Yeah.
So, okay, that was one question. The other thing we definitely wanted to talk about, because, I shot my mouth off last week, and I'll still stand by the Bill Hurd version. But I talked about, using one of these on the scopes, right? And I should preface it by saying I was talking about what I do and how I do it, especially in the old days. But then we talked about, the proper way is to float the scope and the device under test with an isolation transformer. Absolutely, yes. First off, don't take safety advice from Bill Hurd. Just don't, okay? But the second thing, the reason why I float my scope and not my device under test, I'll tell you right up front, is because I trust my scope not to have leakage. Otherwise, I would have been shocked already. And I don't trust the device under test worth a whit. I just know about the leakage currents, especially in the EMI filters and whatnot, is where a lot of that leakage comes from. So I tended to trust my scope not to kill me more than the device under test. So that's why I come from where I come from on that. Whoop, Alan, we lost your audio.
Oh dear.
All right, you should have it back
there.
now.
Yeah, you're back.
Woo,
good.
Okay. So coming from being an employee of a test and measurement company, right? I've got to hold the line and say, don't ever unground your scope or float your scope. But again, if you're applying some logic to this and some thought to this, and knowing that you're not going to do something that's dangerous, you can do what you need to do. Back in the days when we had things like transformerless TV chassis and radio chassis and things like that, and a live metal chassis could be at line voltage, right?
Yeah, it could.
Then it was important to isolate the DUT you're measuring so that you wouldn't get this. If you float the scope and you connect your scope ground to the chassis, and the chassis was hot, now all of the other ground connections on that scope are at line voltage. Okay,
yes.
Right.
So because you have to remember that even if you floated the ground all of these shells of the grounds of all the connectors on the scope are all still at that ground. So if you've elevated that ground by connecting it to somewhere else, you've elevated the entire scope by that much.
Yeah.
So I learned about chassis.
The DUT instead.
When you can do that, you can. But like I said, if it's an issue where you're worried about leakage and things like that, and you know better what's going on, you can apply your own intelligence to it. But the general recommendation is don't float the scope.
So now I unfortunately, or fortunately as it may be, I learned about chassis safety back in those days of where your tube radio could have a hot chassis, because even the prongs weren't standardized to have a big prong and a small prong. If your radio was old enough, it mattered how you put it in the AC plug. And then on top of that, I was doing electronics in my basement on a cold, damp basement floor, and you could get shocked. You'd touch a chassis and feel a tingle, or if you touch the ground pipe, you'd land on your ass. Yeah. So I learned real quick about chassis grounds when I was young.
Oh yeah, well I had a problem. My bench downstairs where I do all my my videos and all. When I first set it up, I'm down there working, I'm doing my thing. And every once in a while, when I leaned my arm on the metal edge of the desk, I'd feel a little tingle.
I was just getting ready to talk about a metal edge story. That's so funny you say that.
Yeah, so because I got an old steel office desk that's got a metal edge, it's a metal desk, and I'd feel a little bit of a tingle. And it turns out the outlet that I had the majority of my equipment plugged into had it was miswired. The ground was there, but neutral and ground were reversed. Right. And I'd get a tingle because my desk was sitting at like 60 volts. So
it forms a voltage divider.
Yep.
Or from inductance, if you probably find you get a bigger voltage on the desk if you have a heavier load plugged in.
Yep. So
yes. When I was 17, I was a TV repairman. And the place my boss had set up as a TV repair shop had been a pizza place or something. And our workbench had a metal strip along the front of it. And mine's not a grounding story, but one day there was two interns in there. And one guy dropped his chassis on the metal part, and the other guy popped off the bench because he caught whatever voltage he just was coupled to the metal. So the next thing my boss hears is me tearing the metal off the edge of because I'm an all or nothing kind of guy when it comes to safety type things.
I worked in a TV repair shop when I was about that age too, so I don't have that story, but I was also in a TV repair shop when I was in high school. So
right, so you know what it's like. Go ahead.
The chat. Tosca was mentioning in the chat some of the tube amps he's repaired had those same plugs, and it just reminded me when my older brother who got me into electronics was a tech for the Australian Broadcasting Commission, and he did a lot of tube amps on the side because being a guitarist and everything, and he gave me an amp to play with this one time. It was a single twin triode, sort of 1 watt amp in the back of the speaker cabinet, about this big, a little tiny thing like a Fender Champ style thing, and I actually got a very big jolt just from the chassis. It was crazy.
Well, Alan, if
anything could happen.
Yeah. Alan, if you remember from the old TV days, then remember reaching way back in the chassis to where the hairs on your arm would stand up as you get close to it. So what I came across earlier when you asked about the probing tools, I still have my old IF transformer adjustment tools.
The diddle sticks, yes.
The diddle sticks, where you would learn the trick of bending it down, because you had to reach between all this high voltage sources, and there wasn't room to stick it in. You learn this actual technique of bending it with your fingers so that it's bent like this. When you put it in and you're turning it horizontal and it's turning. So I still have that technique of, sticking my arm way in or wiring a chassis up in the air.
Yeah, my first jobs at the TV repair shop were, ripping out the tuners and buffing all the contacts.
Yes.
So it's the same thing. You'd reach into a TV that had just been turned off. The second anode voltage on the CRT is still there. So you still kind of feel that tingle when you're reaching in to unbolt the tuner to pull it out to take it apart and buff the contacts of it. So yeah.
So, and we're from the time when banging on your TV set actually worked sometimes for a while. People at home would bang on their set. And what they're doing is they're moving the contacts through. And I've seen where they bang so hard that the tuning slugs came out of some of the channels. You know,
sometimes they bang to clean up the contacts on the switches, or sometimes even knock the tubes around a little bit in the sockets to kind of clean off the oxidation there. So yeah, because it's funny because when you're growing up, you know, you go to turn the channels on the TV and you turn them too fast, and your mom slaps you. You say, just don't take it easy on that knob, right? And as soon as the TV came across the bench, back in the shop, the first thing we did is we spun that thing around like we're trying to start an airplane or something, you know.
Right. And then we get in there with our little greases and cleaners. Yeah. I used to use a pencil eraser, was as good a contact cleaner as anything I found.
Yeah, I used a small Dremel on a speed control and use that to literally go through every contact and buff every contact up. So
go ahead, Ben.
No, it's just saying the eraser trick worked on model railroads too.
Oh yeah,
on the rails.
Yeah.
Shine it up.
So Mike Fikes is asking a question: if you have during the winter, if you have static buildup, is it safe to discharge by touching the scope B and C ground, or is that bad for the scope? So in other words, can you use that as your grounding post for static?
It's a little close to the input. So I'd worry about even a little close to the input. Most of the scopes will also have a separate ground connection just out on the front panel. You could use that. The problem with that though is that, and because that doesn't work exactly the same as an anti-static mat, right? An anti-static mat's got some resistance to it, so that
to keep you from getting killed.
Current. Limits the current for the discharge, right? If you just go directly to ground, you can get a lot of current, a lot of DIDT. A lot of DIDT means, what's the voltage developed across an inductor? It's the inductance times the rate of change of current, right? So L times DIDT. So if I've got some charge built up and I touch a very low impedance, I'm going to get a lot of charge moving very quickly. So that's a lot of DIDT, a lot of rate of change of current that can induce a large voltage in anything that's inductively coupled to it. So while you can get away with it sometimes, it's not the best idea.
Right. So I'll say to the chat room, any final questions? We'll give you a couple minutes to type in. But wow, this is really good. I actually didn't know about the offset function in the digital scope. So I learned
a lot of people don't know that it's there. And you might even remember you might have had active probes in the past that actually had an offset adjustment for looking like at ECL voltages and things like that. But a lot of people don't realize that actually is in many of the digital scopes. So.
Right. And of course, one of the things we talked about today that you don't get, I don't think you get them on analog scopes, what I call them linear scopes earlier, is you don't have the ground reference, that little point. I love that because in the old days, you'd have to disconnect, see where your ground is, reconnect to see, or hit the ground.
The input coupling
ground connection.
Ground point. So you can say, okay, there's ground. Right. Okay. Yeah. There was another function for that too. It would not only show you where ground was, but would also pre-charge the AC coupling capacitor. So if you switch to AC coupling, you wouldn't have to wait for that thing to kind of settle out.
Oh, okay, right.
Yeah.
Right.
So there's so much to scope. They're amazing, and you're never too experienced to learn something new, and they keep getting better and better with what we can do with them. So this.
It's pretty amazing.
Right. Now Ben's got a great answer to the floating ground problem. He has a battery-powered scope.
There you go. Yep.
That's the other way.
Yep.
Yeah. Still don't take it in the bathtub with you.
Still connectors and bits of metal you can touch, so still be careful.
Yeah, because even battery power, now all of the connectors are still connected to each other. There are a very small portion of scopes that are available where each input is truly isolated. But that's it's like there aren't that many scopes that meet that criteria, but there are a couple.
Right.
You're going to pay for it.
Yeah, and they're generally lower bandwidth scopes that are used like industrial, servicing applications. They're not something you typically find in an electronics lab.
Right. So, well, any final words? I mean, this has been great. We're coming up about 12, 13 minutes after the hour here, and
I appreciate it. This was fun. Hopefully everybody got a little something out of this and learned about compensate your probes, find that probe compensation screwdriver, know how to use it, and then understand what the scope is telling you and explore a little bit. And just remember, a lot of people in the comment section said you can't find things in menus and things like that. Just remember that generally things are arranged in a logical fashion, right? Anything that is vertically related, vertical scale, vertical offset, vertical, probe settings is going to be under some kind of a vertical menu, okay? Channel menu or vertical menu. Similarly, there's horizontal and acquisition menus and trigger menus. So it's just a matter of understanding where to go in each of those, because because sometimes the sea of menus can be tough. And I know that that's something that Tech did in the last couple of years with the latest generations of scopes, is to try to have you no more than 2 clicks away from every setting. So
right,
that's pretty good. That's pretty good.
And what I just found on my menu, but I don't remember where it's at, is I had set the labels, but they weren't appearing. You have to be somewhere else in one of the menus that says actually to use labels, and I forget which menu that was in.
Yeah, and
but you see on mine, it did show up finally.
Yeah, unfortunately there's labels you can associate to traces, so they're kind of on the channel menus. But then there's also screen text that you can put anywhere that's not associated to traces, and that's in a different spot. At least on that scope, since I know you've got an MDO3000, I've got one here. That's kind of what that one is. But we've actually done some really cool things on the latest generations of scopes where you can have screen text, you can have arrows and boxes that can be labeled and moved around. But then we have something that we call bookmarks that allows you to place some text and have a pointer that's going off to a waveform at a particular location in time, and you get an actual reading that's live from that point. And you can put as many of those on the screen as you want. So you can have all these little different points that are being monitored and watched live. It's really cool for documenting things.
Right. So my last scope accessory, which you definitely didn't have on the old linear scopes, is a tiny little keyboard with USB, and this plugs in the front of my scope, and this actually used to fit. It doesn't anymore because of where I moved it, but it used to fit right under the scope, so I could just pull it out and type my label names in and whatnot, or my text boxes.
Yep.
So very cool. Good. Well, Alan, thank you so much for joining us today. Right. Ben, great to see you as always, my friend. I don't have anything else other than everybody have a safe weekend. Have a good weekend. Okay. And we'll see you guys. We'll see Ben, you next week. And Alan, we're going to have you back on again if you'd be willing.
Truly awesome. Thank you so much for taking out the time. I know you're busy.
Yeah, well, it got me out of half a meeting, so that was good.
Well, I do just want to take a second in saying thanks again for another great show, but also everyone, Alan has his own channel that's insanely popular and has, if you want to dive into a lot more depth scopes, he's pretty much got everything you need to know there at W2AEW on YouTube. That's his channel. Definitely check that out, subscribe, like his videos, and we look forward to having you back on the Coriolis effect as well sometime soon.
Sure, I'd be happy to.
Excellent.
All right.
Well, thank you again, everybody.